If you're here, you are probably looking for the Swiss map in Go, so you're mostly wondering how does it work, what actually changed, and why. We'll go through all of that step by step, and in the end we'll look into the benchmarks too. Let's start from the beginning. Before 124, a map was an array of buckets, and each bucket could hold up to 8 key value pairs. The recipe is simple. You take a key, run it through a hash function to get a pseudo-random number, use that number to pick up a bucket, and then search inside the bucket. Same key, same hash, same bucket every single time. That's what makes lookups fast. Simple enough until the bucket fills up, and that's where this whole story begins. What's under the hood of an old map? At the top sits one struct called hmap. It's the header for the whole map. It keeps a few important things like count, how many elements you have right now, b, a number that tells you how many buckets exist, and a pointer to the bucket itself, and also a pointer to an old bucket array, which matters later when the map grows. So the map header doesn't hold your data directly, it points to an array of buckets, and the buckets are where keys and values actually live. Think of hmap as the table of contents and the buckets as the pages. Why are there 4 buckets, and what's b? Here's the part that trips everyone up. The number of buckets is always a power of 2, and b is the exponent, not the count itself. So the number of buckets equals 2 to the power of b. If b is 0, that's 1 bucket. B is 1, 2 buckets. B is 2, 2 squared gives you 4 buckets. B is 3, 8 buckets, and so on. Now be careful, because there are 2 different 8s floating around. The 4 is how many buckets you have, that grows as the map fills up. The 8 is how many slots fits inside each bucket, and that one is hard-coded, it never changes. So with b equals 2, you have 4 buckets times 8 slots, then 32 entries before anything overflows. Why a power of 2? Because picking a bucket becomes almost free. Instead of inexpensive division, hash modulo the number of buckets, and Go can do a single bitwise AND operation. Hash AND operation, number of buckets minus 1. That's one CPU instruction instead of slow divide. And as the map gets full, b simply ticks up by 1, which doubles the number of buckets. What's inside the bucket? Open up a single bucket and you'll find there 3 separate arrays sitting side by side plus 1 pointer. First, top hash, 8 bytes, 1 per slot. Second, keys, the 8 keys. Third, values, the 8 values. And finally, an overflow pointer. The important detail, these are parallel arrays. Entry number there is 3. Top hash is the size of 3 plus keys plus values. Same index across all 3 arrays. And here is a question people always ask: why keep arrays and values in separate arrays instead of storing them together like key value, key value? The answer is memory alignment. Imagine a map from 1 byte key to an 8 byte value. If you interview them, the CPU would force each 8 byte value onto an 8 byte boundary, so it would insert 7 wasted pattern bytes after every key. By packing all the key together and all the values together, that pattern disappears. Same data, less memory. So let's talk what happens during collision, chaining, overflow bucket, and why is it bad. So you're filling a bucket and a 9th key wants seen, but there are only 8 slots. They're all taken. What now? Go allocates a brand new bucket somewhere else on the heap and links to it with the overflow pointer. This is called chaining. Keep you colliding and you build a chain, bucket, then overflow, then another overflow, and so on. And this is exactly where it hurts, because those overflow buckets live in random addresses in memory. Your CPU is fast, but main memory is slow, so roughly 100 times slower than its on-chip cache. To hide this gap, the CPU tries to prefetch data, and it thinks that you'll need this next, but it can only predict sequential access. So a pointer to a random address is the opposite of predictable. So every hop down an overflow chain is a cache miss. The CPU just stalls here and waiting for memory. This is called pointer chasing, and at a scales, it's death by 1,000 stalls. Now inside one bucket, how does the lookup actually find your key? This is where top hash earns its keep. Top hash stores the top 8 bits of each key's hash, basically a tiny 1 byte fingerprint. When you search, you don't immediately compare full keys because a key might be a long string and string comparison is expensive. Instead, you first compare that single byte. If the top hash doesn't match, this slot is definitely not yours. You skip it, you never touch the key. If the top hash does match, then it's maybe, so now you compare the full key to be sure. That cheap 1 byte check rules out about 7 of the 8 slots on average, so you almost never pay for an expensive comparison. But here's the catch. Uh, the old map does these checks on one at a time, eight separate comparisons in a loop. The CPU loads memory in 64 byte chunks called cache lines. So all 8 entries arrive together, that the parts is fine, right? The problem is those 8 comparisons are 8 separate instructions and your program shares the CPU with everything else. Between checking slot 1 and slot 2, another thread can run and evict your cache line. When you search resumes, it has to reload from memory. 8 sequential checks means up to 8 chances to get interrupted. What's the evacuation process? Maps don't stay small. Go watches the average number of elements per bucket, the load factor, and once it crosses about 6.5 elements per bucket, which is roughly 81% full, it grows. Growing means allocating a new bucket array within twice as many buckets and moving everything over, but Go doesn't move it all at once. That would freeze your program while it copies millions of entries, and instead it migrates incrementally, a few buckets at a time, one on each insert. The cause of that cleverness during the migration, both the old and the new bucket arrays exist at the same time, so you get a memory spike up to 2 times the memory until the move finishes and the old array is garbage collected. And every single operation has to check both arrays while the migration is in progress. How does Swiss Map solves? And what is an open addressing mechanism? Swiss tables were born at Google Zurich back in 2017, open sourced in C++ and then ported in Go over the next 2 years. And their core decision is a complete change of strategy. Throw out chain and use open addressing instead. The idea is beautifully simple. No linked lists, no overflow allocations, no pointer to chase. Every entry lives directly in one contiguous array. If 2 keys collide, you don't allocate anything. You just probe the next spot alone until you find room. And contiguous memory is exactly what the CPU prefetcher loves. So right away, villain number 1 pointer chasing his gun, but to kill the second villain, the sequential scan, we need to look closer at how a Swiss table is laid out. So, new structure. What's a table, group, control world, and key value? The new map has few levels. At the top is a directory, just an array of pointers that routes you to the right table. Think of it like the index in a phone book. The letters point you to a page, but the actual entries are on the page. Each table has its own independent mini-hash table holding up to 1024 groups. The reason tables are independent is that they can grow one at a time, instead of rehashing the whole map at once. Inside a map, you have groups. A group is the real unit of work, 8 slots sitting in contiguous memory with one extra piece on top called the control world. And a slot now holds up the key and the value together, not in separate arrays like the old map. So once you find your key, the value is right there in the same cache line. We've got the structure, directory, table, group, but how does the map knows which table and which group to go to? That's the hash split. You take the 64-bit hash and slice it into parts, and each part has one job. The top bits pick which table in the directory, a big chunk, call it H1, which picks which group inside the table. And the bottom 7 bits, call it H2, become a tiny fingerprint of the key. Why split it like this? Because each piece needs a different size. H1 has to be large because it's choosing among potentially thousands of groups, and more bits means better spread. H2 only needs 7 bits because it's just a quick filter inside of one group of 8s, and every extraction is just a shift of or a mask, a couple of CPU instruction, no division anywhere. So where does that 7-bit fingerprint actually live?
Every slot in a group has exactly one byte of metadata, and that byte packs up two things: the 7-bit in H2 value and one bit that says whether the slot is occupied. A few special things matter. If the byte is between 00 and 7F, the slot is occupied, and that's the fingerprint stored inside. If it's 80, the high bit set, the slot is empty. And FE marks a tombstone, which means deleted, and we'll come back to that. Now, here's the magic setup. 8 slots per group means 8 metadata bytes, and 8 bytes fit into a single 64-bit word, the control word. And that one word is the thing we're about to compare against all at once. Remember that 8 fingerprints packed into one machine word. Let's talk about the trick of parallel matching and SIMD. This is the heart of the whole design. To find a key, the old map asked, is it a slot 0, slot 1, slot 2, one at a time? The Swiss table asks the question about 8 slots at once. Here is how. You take your 7-bit fingerprint and broadcast it. Copy it into all 8 byte lanes of a 64-bit word. Then you XOR it against the control word. Anywhere the fingerprints match, those bytes cancel it to 0. And one more little bit trick: finds the 0 bytes and out pops a bit mask telling you exactly which slots are candidates. No loop, no branches, all 8 compared in effectively one operation. And it's the difference between a cashier scanning items one at a time and a scanner that reads the whole conveyor belt in a single pass. On modern x86 chips, the CPU does this there literally in hardware with single instruction multiple data, or call it SIMD, in about 3 instructions, roughly one cycle. On other platforms like Apple Silicon, a portable bit trick credited to Jeff Dean does the same thing in 5 or 6 instructions. Either way, villain number 2, the sequential scan, is dead. One small caveat: 7 bits isn't unique, so a match is only a candidate. You still confirm the full one-key comparison, but you've eliminated about 99% of the work in a single shot. How does insert happen step by step in a new map? Let's put all together and insert a key. Say m of hello equals to world. Step 1, hash the key and split it into h1 and h2. Step 2, use the top bits to pick up the table from the directory. Step 3, use h1 to pick up the group. Again, a single bitwise AND operation because the group count is a power of 2. Step 4, run that parallel match for h2 against the control word. If something matches, compare the full key. Maybe you're updating an existing entry. In our case, nothing matches, so this is generally new. Step 5, find the first empty slot. The one marked 80, write the fingerprint into the control word, and write the key and values into one slot together. And that's it. Every step is just shifts, masks, and one parallel compare. But what if the group you landed in is already full? Then you probe to another one. And here's the clever part, not just the next one. Swiss table use triangular probing. You jump one group, then 3, then 6, then 10. Those are triangular numbers, the gaps growing by 1 each at a time. 2 nice properties come out of this. It's guaranteed to eventually visit every group, so you always find a spot if one exists, and it avoids one clustering that simple. Just check the very next slot probing creates. What are these tombstones for open addressing? Open addressing isn't completely free. Deletion gets tricky. Picture 3 keys, A, B, C, and that all landed in one probe chain. Now you delete B. If you just mark B slot empty, you've broken the chain. Later, when you look up C, the search walks along, hits that empty slot, and assumes nothing passed there and gives up, even though C is sitting right there a little bit down. And the fix is a tombstone. Instead of marking the slot empty, you mark it with a special rule called FE that says something was deleted here, but keep looking. Lookups keep past it, new inserts allowed it to reuse it. And the downside is that tombstone pile up in maps with lots of churn, wasting space and slowing probes, so Go periodically cleans them. And this bookkeeping is exactly why in the benchmarks, deletion is the one operation that actually got a bit slower, and an honest trade-off. Most maps in real code are tiny, so Go optimizes for that. A small map, 8 or fewer entries, is just a single group. No directory, no tables, none of this machinery. Only when it outgrows that does it evolve into the full structure. As you keep inserting, the table tracks how much room it has left. When a table fills up, it grows. First by doubling this number of groups up to that limit of 1024. Once a table hits 1024 groups and is full, it doesn't double anymore. It slips into two tables, and crucially, the table that's actually full pays the cost. The rest of the map isn't touched. That's the big win over the old map's evacuation. There is no 2 times memory spike across the whole map and no giant stall. Growth happens in small, bounded chunks capped at a few thousand entries per step. The technique underneath is called expandable hashing, with a directory that doubles and some depth bookkeeping. And the takeaway you can feel is simply smooth, predictable growth instead of one big lurch. So does this old theory actually pay off? Here are the numbers a benchmark suit. Go 123 versus 124 on an Apple M4 Pro chip. Insert with capacity pre-allocated is about 47% faster. A lookup that hits around 10% faster. A lookup that misses, the case where the old map used to walk these long overflow chains, is about 64% faster. Iteration is roughly 15% faster. And there is one regression, and that is the deletion, which is around 58% slower because of all the tombstone bookkeeping we talked about. And then there is memory. A real-world report from Datadog saw one map drop from about 726 megabytes down to 217. That's roughly 63% less memory. You get a higher load factor, 0 less work for the garbage collector. The best part, you get all of these for free. No code changes, no flags, just build with Go 124 or later.